Hello, everyone, and welcome to Chapter 10 on chemical bonding. I'm Dr. Luning He. In today's lecture, we'll explore the different types of chemical bonds, how they form, and why understanding bonding is critical in chemistry, especially for applications in health sciences and nursing. To start off, let's consider a real-world application of bonding theories. Back in 1989, scientists determined the structure of HIV protease, a critical protein used by HIV, the virus that causes AIDS. With this structural knowledge, researchers applied bonding models to simulate how different drug molecules might interact with the HIV protease. What you see on the screen is a visual representation of that protease in gold with a drug called indinavir, a protease inhibitor, shown in the center. This kind of simulation is made possible by our understanding of how atoms. Why is this important? Without the HIV protease, the virus can't replicate. So by designing a drug that sticks to the active site of the protease and disables it, scientists were able to stop the virus from spreading. These medications, called protease inhibitors, became available in the early 1990s and revolutionized HIV treatment. Although not a cure, they help maintain undetectable viral levels and allow patients to live nearly normal lifespans. This is a powerful example of how bonding theories have real life-saving. Now let's talk about bonding theories themselves. These are scientific models that help us predict which combinations of atoms will form stable compounds and which will not. For example, why is salt an ACl and not an ACl2? Why is water H2O and not H3O? These theories also explain molecular shapes, which in turn influence many physical and chemical properties. So bonding theories are more than just abstract ideas. They're foundational to understanding molecular. One of the earliest and simplest bonding theories is the Lewis theory, named after Gilbert Newton Lewis. In this theory, electrons, especially valence electrons, are represented as dots. These dot structures, also called Lewis structures, help us visualize how atoms share or transfer electrons to form molecules. Despite its simplicity, Lewis theory remains extremely useful for making quick predictions about molecular stability and structure, even in clinical or lab. In Lewis theory, we focus on valence electrons, the outermost electrons involved in bonding. We represent them as dots surrounding the symbol of an element. This gives us what's known as a Lewis dot structure. For main group elements, the number of valence electrons corresponds to the group number on the periodic table. This visual representation helps us understand how atoms might interact during bonding. Here's an example using oxygen. Its electron configuration tells us it has 6 valence electrons. So in its Lewis structure, we place 6 dots around the symbol O. We usually distribute the dots one at a time around the 4 sides before pairing them up. This method helps when we start forming bonds later. Each dot stands for 1 valence electron. While the placement isn't rigid, a common practice is to first place single dots on each side of the element's symbol and then pair them. This becomes important when you do your homework, as following this convention helps you avoid mistakes when predicting bond formation. When you apply this dot structure to all the elements in period 2, lithium through neon, you can easily count their valence electrons. Atoms with a full set of 8 valence electrons, called an octet, are particularly stable. This stability is key to understanding why atoms bond the. Let's try phosphorus as an example. Phosphorus is in group 5A, so it has 5 valence electrons. To draw its Lewis structure, we place 5 dots around the symbol P. This visual representation tells us how many electrons phosphorus has available to share or transfer when bonding. Helium is an exception to the octet rule. It only needs 2 electrons to be stable, a configuration called a duet. So even though helium is in group 8a, its Lewis structure shows just 2 dots. For helium, this duet represents a full. Helium is an exception to the octet rule. It only needs 2 electrons to be stable, a configuration called a duet. So even though helium is in group 8a, its Lewis structure shows just 2 dots. For helium, this duet represents a full stable shell. According to Lewis theory, chemical bonds form when atoms either transfer or share electrons to achieve a stable electron configuration. If electrons are transferred, the result is an ionic bond. If they're shared, it's a covalent bond. In both cases, the goal is stability, typically in the form of. Most atoms are striving for 8 valence electrons. This is the octet rule. The main exceptions are hydrogen, lithium, and beryllium, which are stable with just 2 valence electrons. Understanding these patterns helps us predict how elements will. When metals bond with nonmetals, electrons are transferred from the metal to the nonmetal. This forms ions. Metals become positively charged cations, and nonmetals. When metals bond with nonmetals, electrons are transferred from the metal to the nonmetal. This forms ions. Metals become positively charged cations, and nonmetals become negatively charged anions. Their opposite charges attract, forming an ionic bond. In Lewis structures, we represent this by showing electron dots moving from metal to nonmetal. For example, potassium, K, and chlorine, Cl, each have their own Lewis dot structures. When they bond, potassium donates its 1 valence electron to chlorine. This electron transfer allows both to achieve stable configurations. Potassium ends up with an octet in the previous shell, and chlorine now has a full. After the transfer, potassium becomes a positively charged ion K+, and chlorine becomes a negatively charged ion Cl-. These oppositely charged ions attract and form the compound KCl. In drawings, we typically enclose the anion in brackets and indicate its charge in the upper right. Let's apply this to magnesium oxide, MgO. Magnesium has 2 valence electrons and oxygen has 6. Magnesium donates both electrons to oxygen, forming Mg2+ and O2-. Both ions now have full outer shells. This is a typical ionic compound formed by complete electron transfer. Let's look at sodium and sulfur. Sodium has 1 valence electron and sulfur needs 2 to complete its octet. Therefore, 2 sodium atoms are required to donate 1 electron each to a single sulfur atom. This forms 2 Na+ ions and 1 S2- ion, resulting in the formula Na2S. Lewis structures help us visualize and verify this. When nonmetals bond with other nonmetals, they form covalent bonds by sharing electrons instead of transferring them. These shared electrons allow each atom to achieve a stable configuration. In Lewis theory, we illustrate this by showing atoms sharing dots, valence electrons, in overlapping regions. Take water as an example. Oxygen has 6 valence electrons and each hydrogen has 1. To become stable, oxygen shares 1 electron with each hydrogen. Each hydrogen ends up with a duet and the oxygen achieves an octet. This sharing is what forms a covalent bond. Those shared electrons situated between the 2 atoms count toward the octets of both atoms involved. This is the basis of covalent bonding. It's a mutual sharing where both atoms benefit by reaching stability. The electrons shared between atoms are called bonding pairs. Those that belong only to one atom are called lone pairs or non-bonding electrons. To simplify drawings, we often represent bonding pairs as dashes. 1 dash equals 2 shared electrons, a single bond. Let's look at chlorine. A single chlorine atom has 7 valence electrons. If 2 chlorine atoms come together and share 1 electron each, they both achieve an octet. This is why elemental chlorine exists as Cl2, a diatomic molecule. The same applies to other halogens like fluorine, bromine, and hydrogen has only 1 valence electron and it needs just 1 more to form a duet. When 2 hydrogen atoms share their electrons, each gets a duet, making H2 a stable molecule. That's why hydrogen gas exists in nature. Sometimes a single shared pair isn't enough to satisfy the octet rule. Take oxygen as an example. Each oxygen atom needs 2 electrons to complete its octet. When they share 2 pairs of electrons, they form a double bond. This allows both atoms to reach a stable configuration. By converting lone pairs into shared bonding pairs, we ensure each atom has an octet. In the case of O2, a double bond provides each oxygen atom with 8 electrons in its valence. Triple bonds involve the sharing of 3 electron pairs between atoms. Take nitrogen, for example. Each nitrogen atom has 5 valence electrons. By sharing 3 pairs, both atoms achieve octets. This creates a very strong and short bond, characteristic of the N. In general, the more electron pairs shared, the stronger and shorter the bond. For instance, a single OO bond has a bond length of 148 picometers, while a double bond shortens it to 121 picometers. However, Lewis theory doesn't explain all properties. For example, it can't fully explain why O2 is paramagnetic. This limitation led to more advanced bonding. Triple bonds are even stronger and shorter than double bonds. The bond length in N2 is just 110 picometers. Because of this strong bond, nitrogen gas is very stable and relatively unreactive. That's one reason why nitrogen makes up about 78% of Earth's atmosphere. It just doesn't react easily. Let's go through an example of how to write the Lewis structure for carbon dioxide, or CO2. First, we start by drawing the correct skeletal structure. Carbon is the central atom, and the 2 oxygen atoms are placed on either side of it, like this, OCO. Next, we calculate the total number of valence electrons available. Carbon has 4 valence electrons. Each oxygen atom has 6 valence electrons, and since there are 2 oxygens, that's 6 times 2, which is 12. So in total, we have 4 from carbon plus 12 from oxygen equals 16 valence electrons to work with in our. Next, we need to place the 16 valence electrons around the atoms in the molecule. Start by placing electrons as bonding pairs between atoms to form single bonds. This connects the atoms together. Then, use the remaining electrons to complete octets on the outer atoms first. These are usually the atoms on the ends, like oxygen in this case. After that, if there are any leftover electrons, place them on the central atom, carbon in this case. Once all the electrons are placed, check if every atom has a full octet. If not, you may need to form double or triple bonds by moving lone pairs from the outer atoms into the bonding region. In carbon dioxide, we find that carbon only has 4 electrons from 2 single bonds, which is not enough. So we move a lone pair from each oxygen to form double bonds. That way, carbon ends up with 8 electrons and each oxygen also has a full. Now let's look at polyatomic ions. These are charged species made up of multiple atoms. The process for drawing Lewis structures is similar, but we have to account for the ionic charge when counting total valence electrons. Add 1 electron for each negative charge and subtract 1 for each positive charge. Always enclose the structure in brackets and label the charge in the upper right corner. To draw the Lewis structure for the cyanide ion, Cn-, we start with the skeletal arrangement, C-N. Carbon has 4 valence electrons, nitrogen has 5, and we add 1 more for the negative charge. First, assign 2 electrons to the bond between C and N, then distribute the remaining 8 electrons. You'll notice neither atom has a full octet yet, so we convert lone pairs into additional bonding pairs, resulting in a triple bond. Finally, enclose the structure in brackets. Lewis theory is powerful but not perfect. Some molecules don't follow the octet rule. For instance, nitric oxide NO has an odd number of electrons, 11 total. It's impossible for all atoms to have full octets. In such cases, we write the best possible structure. Another common exception is boron, which often forms compounds like BF3 and BH3 with only some atoms, particularly those in period 3 and beyond, can have more than 8 electrons. This is called an expanded octet. Examples include SF6 and PCl5. While we won't cover expanded octets in depth here, it's important to be aware of them. Even with these exceptions, Lewis theory remains. Sometimes more than one valid Lewis structure can be drawn for a molecule. Take SO2, for example. Both SO double bonds could be placed on either side. These are called resonance structures. The actual structure is an We start by assigning electrons between atoms and then distribute the remaining electrons to terminal and central atoms. If the central atom lacks an octet, we form a double bond. Either oxygen can form the double bond, and both. Although the Lewis structures show 2 distinct bonding patterns, the real molecule is not switching back and forth. Instead, it exists as a resonance hybrid, an intermediate where both bonds are. If we believed only one of the resonance forms, we'd expect one double bond and one single bond. But experiments show both SO bonds are equivalent, falling between the lengths of single and double bonds. This supports. To represent this more accurately, we use a double-headed arrow between the resonance structures. This notation tells us the molecule doesn't flip between them. It exists in a stable average state. Resonance is key for understanding molecules like ozone, nitrate, and many. To go beyond Lewis structures, we use Weissenper theory. To go beyond Lewis structures, we use Weissenper theory, valence shell electron pair repulsion. This theory helps us predict molecular shapes based on the repulsion between electron groups. These groups, whether lone pairs or bonding pairs, try to. Let's apply Vcpar to carbon dioxide. CO2 has 2 double bonds around the central carbon atom. These 2 electron groups repel each other and spread out in a straight line. The result is a linear geometry with a bond. Let's apply Vcpar to carbon dioxide. CO2 has 2 double bonds around the central carbon atom. These 2 electron groups repel each other and spread out in a straight line. The result is a linear geometry with a bond angle of. H2CO, or formaldehyde, has 3 electron groups around the central carbon, 2 single bonds and 1 double bond. These groups arrange themselves 120 degrees apart, forming a trigonal planar shape. While the ideal bond angle is 120 degrees, the double bond to oxygen contains more electron density and repels more strongly than single bonds. As a result, the HCH bond angle is slightly compressed to about 116 degrees, while the HCO bond angle expands to about. When a molecule has 4 electron groups around the central atom, like methane CH4, they arrange themselves in a tetrahedral shape. This geometry spreads the electron groups as far apart as possible, creating bond angles of 109.5 degrees. This minimizes electron repulsion and stabilizes the molecule. geometry clearly. Now let's see what happens when lone pairs are present. In ammonia, NH3, there are 4 electron groups, 3 bonding pairs, and 1 lone pair. The electron geometry is still tetrahedral, but the molecular geometry is trigonal pyramidal. The lone pair repels the bonding pairs more strongly, slightly In water, H2O, there are again 4 electron groups, 2 bonding pairs and 2 lone pairs. The electron geometry remains tetrahedral, but the molecular geometry is bent. The lone pairs push down on the bonding pairs, reducing the bond angle even further. That's why water has a bent shape. This slide likely presents a summary diagram of common molecular shapes based on electron group arrangements: linear, bent, trigonal, planar, tetrahedral, and trigonal pyramidal. Take time to memorize the link between the number of electron To predict molecular geometry using VCPAR, follow these steps. First, draw a correct Lewis structure. Then count the total number of electron groups around the central atom, separate bonding groups from lone pairs. Finally, use these numbers to determine both the electron geometry and molecular geometry. When drawing molecules in 3D on paper, we use specific bond notations. A solid wedge represents a bond coming out towards you, while a dashed wedge represents a bond going away from you. Regular lines stay in the plane of the paper. This notation helps convey the This slide shows examples of molecules in 3D notation, like tetrahedral CH4, trigonal pyramidal NH3, and bent H2O. Use these illustrations to practice visualizing molecular shape. Let's connect shape to something we experience daily: taste. Artificial sweeteners like aspartame taste sweet because they mimic the shape of sugar molecules. Our taste receptors are highly shape-specific. Even though these molecules may not provide calories, they fit into the same receptor pockets as sugar. Taste receptors on your tongue work like molecular locks. If a molecule fits just right, like aspartame or saccharin, it triggers the sweet response. These sweeteners often bind even more strongly than sugar itself, which is why they're hundreds of times sweeter. Understanding molecular shape allows us to engineer compounds with specific. Let's now explore molecular polarity. When you pour oil into water, they separate into distinct layers. Why? It has to do with the molecular polarity of water and oil. Water molecules are polar and strongly attract each other, pushing non. Take a look at the OH bond in water. Each consists of a pair of electrons, one from oxygen, one from hydrogen. But oxygen doesn't share equally. It pulls the electrons closer to itself, creating an imbalance. This is the root. This unequal sharing is due to electronegativity, the ability of an atom to attract electrons in a bond. Oxygen is more electronegative than hydrogen, so the shared electrons spend more time near the oxygen atom. This creates a partial negative charge on oxygen and a partial positive. The result of this unequal sharing is a dipole moment, a separation of charge across the bond. We represent this with the delta symbol, delta negative on the more electronegative atom and D plus on the less electronegative one. The result of this unequal sharing is a dipole moment, a separation of charge across the bond. We represent this with a delta symbol, delta negative on the more electronegative atom and delta plus on the less electronegative one. The OH bond. Covalent bonds with dipole moments are called polar covalent bonds. The greater the electronegativity difference between the atoms, the more polar the bond. For the same bond length, a larger electronegativity difference leads. The concept of electronegativity is based on a relative scale. Fluorine is the most electronegative element with a value of 4.0. The concept of electronegativity is based on a relative scale. Fluorine is the most electronegative element with a value of 4.0, as assigned by Linus Pauling. Other elements are assigned values relative to this standard. The farther right and higher up you go on the periodic table, the more electronegative the element. Here's another reminder of the periodic trend. Electronegativity increases as you move from left to right across a period and decreases as you move down a group. This trend helps us predict bond polarity in different chemical. If two atoms have identical electronegativities, they share electrons equally. That means there is no dipole moment and the bond is considered pure covalent. A good example is Kiel2, where both atoms share the bonding electron. When the electronegativity difference is very large, as between a metal and a nonmetal, the electron is fully transferred from one atom to another, forming ions. This results in an ionic bond. Sodium chloride, NaCl, is a classic example. Na donates. When the electronegativity difference is very large, as between a metal and a nonmetal, the electron is fully transferred from one atom to another, forming ions. This results in an ionic bond. Sodium chloride, NaCl, is a classic example. When the electronegativity difference is very large, as between a metal and a nonmetal, the electron is fully transferred from one atom to another, forming ions. This results in an ionic bond. Sodium chloride, NaCl, is a classic example. Na donates. Between these extremes is an intermediate difference in electronegativity, typical of bonds between two different nonmetals. The electrons are shared but unequally. This results in a polar covalent bond. For example, in HF, the electron pair is more likely to be near. Bond type isn't always black and white. It exists on a spectrum. This slide provides a rough guide. 0 to 0.4 means nonpolar covalent bond. 0.4 to 2.0 indicates polar covalent. Greater than 2.0 indicates ionic bond. These are approximate but helpful. Here's a common question. Does having polar bonds mean the whole molecule is polar? Not necessarily. For a molecule to be polar, the individual dipole moments must not cancel out. In some geometries, like linear or symmetrical molecules, the dipoles cancel, resulting in a nonpolar molecule, even if the. Let's look at CO2. Each CO double bond is polar due to an electronegativity difference of about 1.0. But CO2 is linear, so the dipoles point in opposite directions and cancel each other out. The result? To visualize dipole moments, we use arrows, vectors, pointing toward the more electronegative atom, the one with delta minus. The tail of the arrow has a plus sign, representing. To visualize dipole moments, we use arrows, vectors, pointing toward the more electronegative atom, the one with delta minus. The tail of the arrow has a plus sign, representing delta plus. If these arrows are equal in magnitude and opposite in direction, they cancel out. In contrast, H2O has polar bonds and a bent geometry. The dipoles don't cancel, they reinforce each other. That's why water is a highly polar molecule. This polarity is critical for its role as a universal solvent and for the behavior of biological. This slide shows a summary chart that helps us understand how to combine dipole moments to decide if water is polar, oil is not. Polar molecules interact with other polar molecules, just like magnets attract. Nonpolar molecules don't mix well with polar ones. So when you try to mix oil and water, the polar water molecules clump together. This slide illustrates intermolecular attractions, specifically how polar molecules align to maximize attraction between their positive and negative ends. This is the basis of hydrogen bonding dipole-dipole interactions and why polar substances dissolve. Here's a practical application. After eating greasy food, your hands are coated with nonpolar grease. Water alone doesn't remove it because water is polar. Soap molecules solve this by having two ends, a polar head that interacts with water and a nonpolar tail that interacts with grease. This dual nature lets soap molecules surround grease and allow. To wrap up, Lewis theory helps us understand bonding by showing how atoms transfer or share electrons to reach stable configurations. Ionic bonds involve transfer, covalent bonds involve sharing. Weierstrass theory then helps us predict molecular shapes based on electron repulsion. These shapes influence a compound's reactivity properties. As we continue our review, let's focus on electronegativity. This property measures how strongly an atom attracts electrons in a bond. It increases as you move from left to right across a period and decreases as you move down a group in the periodic table. Understanding this trend helps predict bond polarity. When two nonmetals with different electronegativities form a bond, the electrons are shared unequally, creating a polar covalent bond. In diatomic molecules, this always results in a polar molecule, but in larger molecules, the overall shape matters. Sometimes the dipole moments cancel out, resulting in a nonpolar molecule despite the presence. Here's a recap of what you should now be able to do. Write Lewis structures for individual elements. Draw Lewis structures for ionic compounds. Use Lewis theory to predict correct chemical formulas. Construct Lewis structures for covalent molecules. Write resonance structures for applicable compounds. Predict molecular shapes using Weierstrass theory. Determine whether a molecule is polar based on bond. Let's end with an intriguing application. Free radicals are molecules with an odd number of valence electrons, leaving one electron unpaired. These species are highly reactive and have been linked to aging and disease. They can damage DNA or cell surfaces, triggering immune responses or even leading to cancer. Understanding their Lewis structures helps us visualize why. Here are some examples of free radicals O2-, O-, O, and CH3OO. Each has an unpaired electron. Try drawing their Lewis structures. Remember, the unpaired electron is placed alone. These unstable species play a big role in oxidative stress, making their study important in both chemistry